Now we've painted ourselves into a little bit of a corner because we have two notions of rank. On the one hand, if we have a linear map from V to W, we've defined the rank of the linear map to be the dimension of the image of that map. On the other hand, if we have a matrix A, we've defined the rank of A to be the dimension of the row space of A. Or we've seen that this is always equal to the dimension of the column space of A. Right? So there are two things that, if you have a linear map, there are two things that you might think are entitled to be called the rank of the map. On the one hand, it's the definition, the rank of F. On the other hand, we have this matrix that represents the linear map F, and it has a rank. So, if there's any justice in the world, these two ranks should be related. In fact, really they ought to be the same, right? If this is going to make any sense. So let's check. Let's check if they are the same. To do that, let's remember this diagram that we've set up where we have our domain space V, we have a function, our linear map, and our codomain W. Rep B is an isomorphism to Rn. The matrix rep BD of F, right? That's a matrix that, acting by vector matrix multiplication, takes us from Rn to Rm. And the last side of the square is rep D, right, which is an isomorphism from W to Rm. And we have shown that we've sort of cooked up all the definitions so that rep D composed with F, right? So if you go this way then that way, that's exactly the same function as multiplying the matrix rep BDH by rep B, right? So So this is what we have to work with, right? And we're hoping to show that the rank of F is the same as the rank of this representation matrix. And just so I don't have to write this out, I'm going to call this representation matrix A, because I like to be lazy. So what is the rank of F? Well, by definition, the rank of F is the dimension of the image of F, right? But this has to be the same as the dimension of the image of F, rep D composed with F. And the reason is because rep D is an isomorphism, right? So if you since rep D is an isomorphism, it can't sort of collapse down. It can't collapse down any more vectors, so it can't make the image any smaller. Of course, it can't make it any bigger either because it's a function, right? So, so the dimension of these has to be the same. There's a slight detail in there that I could make precise, but I think I've made the idea clear enough. So. But now, right, now that we have rep D composed with F, now we can use this. So this is the dimension of A, our representation matrix, composed with rep B. Okay, but rep B is an isomorphism, so rep B isn't going to change the dimension of anything. Oh, I've left off my image. So this is dimension of the image of A composed with rep B. Okay, there we go. But rep B is an isomorphism, so it's not going to change the dimension of anything. So this is the dimension of the image of A. And when I say the dimension of the image of A, what I mean is A acting as a linear map from Rn to Rm. But remember something about how this is defined. So if we have a matrix A11 to A1n down to AM1 to AMN times a vector, say C1 down to Cn, one way to write what this is C1 A11 down to AM1 plus dot 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 down to Cn times A1n down to AMN. Right? In other words, well, what is this? This is just all linear combinations of columns from A. So the image of A as a linear transformation from Rn to Rm, the image of A is exactly the column space of A, right? Because here we've exhibited what can you get by doing this matrix vector multiplication. You get exactly the same thing as all linear combinations of the column of A. So the image of A is really the column space of A. And what is the dimension of the column space of A? It's the rank of A. And so we're done, right? These two are the same, right, through this whole long chain of reasoning. And notice that we really did take advantage of the fact that these two ways of going around this square give us the same thing in the end, the same function from V to Rm. Right? We use that right here because we switched rep D composed with F to A composed with rep B. So the fact that these two are the same really was important. It made this whole thing go.